Hello. In today's video, I'm going to show you guys how you go about um, kind of figuring out how to do this week's lab, since this is our first lab that you guys are going to be doing on your own. So we're looking at the dissociation constant of a weak acid. So, excuse me, a weak acid, when it's added into water, is going to completely dissociate to produce hydronium and an anion. So, the general equation for this is HA AQ plus H2O, liquid, goes to H3O plus AQ plus A minus AQ. Another way that I write it a lot is HAN AQ. They're both just a weak acid, a way of looking at a weak acid. So our weak acid will partially dissociate, which is why we have an equilibrium arrow. This is going to be different from a strong acid, where we take our HA plus our water, and we have a full dissociation to hydronium and our A minus. I will use AN in this PowerPoint to differentiate between a weak acid, so my HAN is going to be weak in this particular PowerPoint, where HA is strong. So you'll see it both ways, but we'll just go with HAN for weak acid in this PowerPoint. Now, when we have a weak acid that gets dissociated, it has an acid dissociation constant associated with it, which we call Ka. So it's our acid dissociation constant. And it tells you about how much of your acid itself has dissociated, giving hydronium and your anion. This Ka, for most, if not all weak acids that are known, we have a Ka value known for that. So if you already know that Ka value, you can go back and calculate out how much of your hydronium, how much of your anion, and how much of your weak acid you actually have in solution. Now, in this lab, we are going to actually be solving for our Ka. So you could either have to know these concentrations already, or you go the roundabout way where you take your pH of your solution to solve for your hydronium concentration, which will then go into a rice table to solve for these other concentrations. And that's what we're going to do today, is to solve for our Ka value. Now, the best thing to do is to take several measurements so you can get several Ka values, and you can then average them. That's going to give you the most accurate results that will take out a lot of the error that you get with your pH probe, with just doing dilutions incorrectly, stuff like that. But that takes a lot of work to do a bunch of different concentrations of your weak acid. So instead, we're going to do a partial dissociation of our weak acid. So we're going to take our weak acid and we're going to add in sodium hydroxide in limiting amounts, which will cause some of this weak acid to react, and some of it will be left over to dissociate. So we'll have some left over, which will then go through a dissociation process like we expect it to. And if we do differing amounts of our if we do differing amounts of hydroxide, we will get differing amounts of our hydronium, and then that will give us differing amounts of everything else. So that's exactly what we're going to do. We're going to take the same amount of our weak acid solution and add in different amounts of our sodium hydroxide. So Dr. Meyer has already done all of this for you guys. So he took 5 well plates, A1, B2, A3, B4, A5. He staggered them, so when he put the pH probe, he didn't cause any spillage into a different well. But You guys know, hopefully remember a well plate from our Le Chatelier's principal lab. It looks something like this. So he used rows A and B. And like I said, he did this so that he could stagger these and make sure he didn't get any leakage into other wells. Okay, so he went through, added different amounts of sodium hydroxide, the same amount of the weak acid, and then differing amounts of water so that the total volume would be 2 milliliters. So each one of the wells has the same volume, so we don't see any volume effects. And then we are starting out with a high concentration or high amount of sodium hydroxide and going down to a lower amount. So we are going to dissociate the most amount of this weak acid, and then this will have the least amount of it dissociated, so there'll be a greater hydronium concentration left over. He then went through and took the pH values for each of these, and this is what values he got. He got 4.66 for A1, he got 4.50 for B2, he got 4.20 for A3, he got 3.89 for B4, and 3.67 for A5. His starting concentrations of acetic acid, which is the weak acid he used, were 1.00 molar, and then his starting concentration of sodium hydroxide, 0.50 molar. Okay, so these are the values he actually got, these pH values, from these concentrations. That's a 0, sorry. So, with this information, you guys should be able to do the whole lab. I will very quickly go over an example of this so that you guys know how to do the calculations. I will, however, be using different initial concentrations of my weak acid and my weak base. Sorry, my weak acid and my strong base, in order to not give you the exact answer, but to give you a template from which you can solve for the answers yourself. So instead of using 1 molar weak acid and 0.5 molar sodium hydroxide, I use 0.95 molar acetic acid and 0.51 molar sodium hydroxide. So we're going to look at well A1. Well A1 had a pH equal to 4.66. It had a HA volume equal to 0.70 milliliters. It had a sodium hydroxide volume of 0.80 milliliters, and it had a water volume of 0.5. Wait, let me look at that. 0.50. Yep. So our total well volume was 2.00 milliliters. We want to convert all of this into liters. So we have 0.0007 liters of our weak acid. We have 0.0008 liters of our strong base, sodium hydroxide, 0.00050 liters of water, and 0.00200 liters of our total well volume. We then want to solve for our weak acid amount of moles and our sodium hydroxide number of moles by multiplying our volume of our weak acid by our concentration of our weak acid. And we do this, we get 0.000665 moles of our weak acid, and we get 0.000408 moles of our sodium hydroxide. Okay, now we're doing a partial dissociation, so we are going to react the sodium hydroxide with the acetic acid, and it's going to react completely. So we start out with 0.000408 moles of our sodium hydroxide and 0.000408 0.000665 moles of our weak acid, acetic acid. We're going to put these into a BCA table before, change, and after, and we're going to see how this changes. Our sodium hydroxide and our acetic acid are in 1-to-1 mole ratios. Since we have a strong base, this is going to react completely. So we're going to do minus 0.000408 moles here. And we're going to do the same thing, minus 0.000408 moles here. Keep in mind your BCA table is always in moles. Okay. Whatever we minus from our reactant side, we're going to add to our product side. So we add 0.000408 moles here. And when we divide or subtract this all out, we get 0 here, 0.000257 moles here, and 0.000408 moles here. Note that if you have done this correctly, you will not have a negative value anywhere, so you know that you have done it correctly. If you do a BCA table and you get a negative value, you've chosen the wrong limiting reagent. You need to choose the other one. Okay, so now we know how many of our sorry, one second. So now we know how much acid is left over. So we have 0.000257 moles of our acid left over. And we want to figure out what our concentration is. So we're going to take the 0.000257 divided by that 0.002, and we get 0.1285 molar weak acid after dissociation. Excuse me. And then if we look our weak acid or our conjugate, we have 0.000408 moles there. Divide that by our total volume, and we get 0.204 molar of our conjugate. We're going to then put this into a ice table or rice table. So we're going to put our initial concentrations. So these have to be in concentration. So our rice table is in concentration, BCA table moles. So our initial concentration of our weak acid after neutralization is 0.1285. We don't know, or we have not dissociated anyone, so we have a 0 for our hydronium. And then we have 0.204 molar of our conjugate. We're going to minus x plus x plus x, giving us 0.1285 minus x, and then 0.204 plus x. After we've done this, since we do not have our dissociation constant, we need to use our pH. So we need to use our pH in order to solve for this, and then we will know what our x value is. So keep in mind that our x is equal to our hydronium concentration, and we can figure out our x by using our pH. So our pH in this well was 4.66. So remember, pH is equal to negative log H3O plus, or H plus, which can be rearranged into 10 to the negative pH is equal to our hydronium concentration, or H plus concentration. So we're going to take 10 to the minus 4.66 And we get a hydronium concentration equal to 2.19 times 10 to the negative 5 molar. So, putting this back into here, we have 0.1285 minus 0.0000219, which basically doesn't change that at all. So we're going to keep it as this value right here. The only value it really changes is this one. So we can then put this into our Ka, where our Ka is equal to our hydronium concentration, 2.19 times 10 to the negative 5, times that by our A minus concentration, 0.204. Again, if we subtract 0.0000219 from 0.204, it's not going to make any difference, so we're not even going to do it. And then our last concentration, 0.1285 for our strong or weak base, weak acid. Okay, then we multiply all this out, and we get a Ka value equal to 3.47 times 10 to the negative 5. Again, those values are not going to be very similar to yours because I'm using made-up concentrations. But that is how you will go about solving for those problems. And that is everything. I hope that helps you guys complete this lab. If it does not, or if you need any additional help, I will have my office hours from 10 until 11:30, Monday, Wednesday, Friday. So please come onto Microsoft Teams. You can do it from your phone, or you can do it from your laptop or tablet or whatever. Um, you don't have to necessarily download anything. You can just do it directly on the web. Just make sure that you have gone through the steps to see information about the Microsoft Teams in case you guys have any questions about this. Okay, that's everything for me. I will see you guys later. Please email me if you guys have any questions. Okay.